All right, welcome back to the Kitchen Research Group. Today I have a new paper that we published on chemical properties from graph neural network predicted electron densities. This work was done largely by Ethan Sunshine in collaboration with the FAIR group at Meta, Mohammed and Zach through the Open Catalyst project. So in a nutshell, what we aim to do here is take an atomic structure like this. This is something you would set up for a DFT calculation or a molecular simulation of some kind. Then build a graph representation of the structure and train a graph neural network so that it can predict the electron density. Normally we would do DFT for this, but DFT is quite expensive and it would be really nice to have a machine learned model that can give us the electron density for several reasons. One is if it's efficient, we can use it to speed up DFT. I'll talk about that in a little bit. And then we can also use it to calculate other properties like partial charges and dipole moments. So if we could combine this graph neural network structure to density, we could combine it with other graph neural network models of energy and forces to get properties related to charge and dipole moments. All right, the data set that we chose came from the OC20 data set in the Open Catalyst project. We pulled about 33,000 structures containing 55 different elements, and they had sample sizes from 9 to 225 atoms. So these were all different kinds of slabs with adsorbates on them that contain all of these metals, and the electron density we got from the charge car files that were calculated using VASP. So that is the data set that we used for training, and it was split into a train test set like the normal way, and you can read about it in the paper. The GNN is basically it's a Schnedt model, but we modified it in a couple of ways. One is we add extra probe points around the atoms. So we have a regular graph that represents the atom, and the edges represent something like the connectivity or bonds between atoms. But we have a second set of probe points that we use to estimate the density at. Now the probe points don't pass any messages, and that's important because there's a lot of them. There's typically 5 million probe points per sample that we need to predict the electron density at, and this is that would be intractable to pass messages between all of them. These only get messages from the atoms to develop the features necessary for the fitting. Then we did two other things. If a probe point was too far from an atom, we set the electron density there to be 0. It's usually very small, and 0 was a convenient choice to make. And then we also enforce conservation of charge. So eventually we are making a prediction at all of the points, and then that is giving us the total density. But we then afterwards enforce a conservation of charge so that we get the right number of electrons when you integrate over that density. And that's important because you don't want your electron number to be changing as you go in most cases. All right, the results are shown first here. This is a kind of parity plot. Maybe we'll start on the right here. The standard way we would make an initial guess for an electron density is a superposition of atomic charge density. So we take the isolated atoms, we know what the electron density for an isolated atom is, and then you put that on top of the position, and you just sum it all up. And compared to the ground state electron density, the error here is about 8.3%. So it's not actually as large as you might expect, but going from 8.3 to 0 is what costs us all the time in DFT. After we did our training, the best model we got was a mean absolute error of 2.54%, and there's a number of differences between the graph on the right and the graph on the left. So on the right, you can see we have a much sharper sort of red center line. Those are the highest density points, and you see a very good parity line out to about 10 to the minus 4 of electron density. And that's a much tighter line than you can see on the right. Once you get in this low density region, a number of things limit the accuracy. One is, again, we set some points to be 0 once they got far enough away, and 0 is not on this log-log plot, so you don't even see them. And the other point is that the high density points are more important in this metric for training than the low density points. But overall, we got to about 2.5% error on that. Now, that's not as low as we hoped, but it turns out it's still useful. So the second result that we did was to take those densities and compare them if we calculate Bader charges, which is a way of partitioning charge into atomic basins, and dipole moments. So compared to using the superposition of atomic charge density, the errors are quite large when you use that for Bader charges. They're quite low when we get down to the predicted ones, something like 0.1 electrons per basin. And what you can see in this kind of learning curve is this is the errors as we increase the size of the data set from 1,000 up to 33,000. And you can see the errors are going down. And that's an indication that our model would get even better if we had more data. But we're practically limited. This is about half a terabyte of data, and the training time is quite substantial and sort of at the limit of what our machines were able to do. So going much larger would require some dedicated effort in the future. The dipole moments also look better. So again, we get kind of modestly large errors for SACD, and that's why we use density functional theory in the first place. And we see that for the most part, the errors go down, at least if you look at the tails. The averages are a little bit tricky. But you can see that the machine-learned predicted densities are actually pretty useful already for calculating some of these chemical properties, even though these were not properties that we trained the model to do. We originally thought we would be able to use this to speed up DFT. So when you start a DFT calculation, you have to initialize the density, and then you use that to calculate all of the things in DFT that are needed. And in conventional wisdom, a better guess would lead to faster DFT calculations. It turns out it's not quite that simple, at least in VASP. You also need some additional augmentation occupancies, which we didn't have a good way to generate. And so what you can see on the right is sometimes we got some calculations that ran faster with the predicted density using a simple way of estimating the augmentation occupancies. But for the most part, we did not get much faster than the SACD. Now, this also has some subtle points. It is possible that the optimization algorithms that are used for this are optimized for the SACD, and they just don't work as well as they do for this predicted ones. Or there's some subtleties in the predictions that actually make it not as good as we would have hoped. So there is potential to get better agreement there, but you can see from here to this bar of 1, which is what you get when you use the perfect density and the perfect augmentation matrix. There's only maybe about a 50% improvement to get here. So it's not obvious to me that it's worth a huge effort to get there. There are some limitations. The densities are probably only reliable for systems like OC20. Those are mostly metallic, intermetallic types of slabs. There aren't any metal oxides, for example. There are no things like zeolites. And so I wouldn't expect that those systems would have particularly accurate electron densities with this, because they would be considered out of domain for that. Now, it does seem possible and probable that you could add that data in, train your model, and be perfectly fine doing that. But since it's not in our train set data, it's probably, the results we have are probably not good out of that domain. And it takes about 1 to 2 minutes on a GPU to predict the density. That's because there's a large number, 5 million-ish probe points, and you have to do them in batches to fit it in the memory on the GPU. So an algorithm that didn't require that was more efficient, would probably be quite beneficial. And finally, it does seem like more data is needed, but again, as I mentioned, we already had something like half a terabyte of training data, and that's close to the practical limit for us. So we would either need some much more clever sampling method or much more efficient way of handling the data to move on. All right, and so in summary, it's certainly possible to use message passing GNNs for predicting electron density. They're accurate enough to get pretty reasonable estimates of atomic charges and dipole moments, I think there's still a lot of room for improvement in the models for the accuracy and performance, and probably more efficient models and larger data sets are still needed to push this particular approach forward. So that's it in a nutshell. The paper is available online. You can find it in the video description, and I hope you enjoy it, and we'll see you next time.